Okay. Good morning, everybody. I'm Alessandro Bicciato. I come from Foscari University of Venice. Today, I'm going to talk about interpretability of graph neural networks. Interpretability of graph neural networks is my main research topic. I started my PhD in 2020. I came from computer science background. I did my bachelor and master at Foscari. My supervisor is Professor Andrea Torsello. During my studies, I visited for my master thesis the University of Toronto, and recently I did my period abroad at the University of York, in which I started a project with them. So as I said, I'm working generally with graph neural networks. These are some of my works, starting from graph augmentation, and I worked a lot on graph kernels. And now I'm working on variational graph autoencoders. For today, I will give a brief introduction on what are graph neural networks. I think most of you don't work with. Then I will explain the project I worked on. So let's start with graph neural networks. Graphs can be a powerful abstraction. Is a structure that can apply to a lot of environments, like chemical compounds, shapes, and also social networks. Most what we can ask to graphs is just like these chemical compounds are toxic or not. This is a shape of a dog or a cat, or what is the correspondence between the vertices of these meshes. However, when we apply machine learning to graphs, we have several challenges. We don't know the order of the nodes because there isn't any, and graphs can have different sizes, and so this can be unfeasible to apply standard machine learning techniques because we have an obvious way to embed graphs in the vector space. So recently, in the last decade, I would say, the graph neural network gained increasing popularity because now we have a method to apply these new learning techniques that are summed in just a convolution operation. This came that a new branch of machine learning was formed, that is deep learning. Basically, we have that artificial intelligence is seen as a way to perform, to give a computation to a machine in a human-like way. We have the subset of machine learning that correspond to explicitly learn something by the machine, and then with an already set of features, and the deep learning techniques stand on the machine learning because they can just learn by themselves. Learn by themselves means that, for example, with machine learning, we have some users that extracted some features that then be classified. For example, in this, we have a feature extracted from an input of a set of cards and others, and we can classify if an image is a card. In deep learning, we don't have this such a step because the neural network can learn how to identify from the feature that can be a car or not a car. So deep learning was used and is currently used on several fields. Computer vision, natural language processing, and speech recognition are the most famous ones. And however, the learning techniques come with downsides because we need powerful computers, and there is always the potential of overfitting our models, just like machine learning. And also there is a problem when we have complex models that can limit the interpretability. So this is my first project, GAMS, graph augmentation with model swapping. It's a deep learning algorithm that was designed for the graph classification task. And the idea consists of a composition of motifs. So it is divided, we can divide the algorithm in three different parts. The motif division, in which the algorithm extracts for each graph in the dataset some cluster with currently we support all the scikit-learn clustering approaches, and the most feasible one for the dataset used was the spectral clustering. Then we have the selection. In the selection, we start from all the cluster that we have. We choose a pair of graphs, and we compute the spiral Riemann isomorphism test, in which we came up with a matrix of similarities between the different clusters in the graph, and we can select the most similar. In the third and final step, we just swap. We want to swap this cluster found to have two more graphs. To doing so, we compute the int kernel signature on each node. These allow us to have the best possible pair with the nodes of each cluster to do the connection between the output, the other part of the graphs. And then we will repeat all the pairing for all the graphs that we want to achieve. These are some results. We did the augmentation on these graph datasets, and we then computed a graph classification, classical graph classification algorithm. In red, here is not very visible. In red, we have the baseline, and then we can see that our augmentation provides better results. until we can see, for example, on the dataset MSRC21 on the far right, that we just arrive for a saturation of the accuracy. Then my other project was on graph kernels. I spent most of my second and third year on this. So our motivation for graph kernels is that they provide an elegant way to bypass the embedding problem that I said earlier. And we can see as a pairwise similarity measure between graphs that is needed to train the model. So the idea was that the convolution can be seen as a message passing strategy, where node features are propagated over the graph to capture node interaction. You can see, for example, here from a layer to another, that is written here in white, we can just propagate our information, and then on the next layer we can add that our initial node have gained information for the neighbors one. So we can argue that these graph kernels can be seen as a natural extension to convolution. Because on convolution, we perform a dot product between an input matrix and a filter. On the graph kernels, we can represent the inner products as an high-dimensional space. The architecture is quite complicated. So for most graph, this is the architecture of our algorithm. For most graph kernels, including the spiral lemon, that is the most classic one, we work with discrete node labels. This architecture works with an m-dimensional real value vector for each graph node. This means that we have to discretize the output feature space before being able to perform filter convolution operation. And before each convolution layer, except for the first one, we add a vector quantization operation to the input node features. So in our implementation, we compute only the gradient with respect to the mask on the current layer, and then we have the final graph embedding after a layer that is obtained by aggregating the concatenation of the output feature node-wise. We have, in the end, a pooling operation that usually we use some pooling operation, but we can also use a mean pooling operation, and then we have a multi-layer perception layer. An extension of this work that basically used the graph kernel to look at the structure of the graphs is the features of alignment. We wanted to apply this message passing mechanism to the node feature of the graphs. So we came up with this architecture in which we apply several times as a layers these FSA features of alignment layer. The architecture is quite similar to the previous one. We construct an egonet of radius R around it. An egonet is just we focus on a node. For example, this one we say we want an element of 1, we just include we extract a subgraph that is of distance 1. And also we maintain all the links between the neighbors. For example, if focusing on this one, if we add another link here, we would preserve also this link. And so for each node, in the eigenet, we compute the dot product of the node features that with a set of features that is also learned during the process. And the maximization of the similarity is propagated, is computed in every node of this eigenet, and then is propagated back to the center of the eigenet. And so we learned from centered on, we learn in this node our feature set. A further extension, because we can go on and on, is the histogram intersection, histogram kernel intersection. Basically, we want to extract the distribution of features in the eigenet for each local neighborhood. I compute them against the set of learned neighborhood distribution, but this time by taking the histogram intersection kernel. This is an example of how the architecture works. We start every time from each node and we extract a subgraph in the eigenet, this example of one hop. Then we have a dictionary that is learned during the process, and also we have these node we have also attached these node features of in this case they are 6 node features by the 5 nodes that we are looking at. From this, we compute the soft histogram for each node, and in the end, we sum all the histogram. We sum all these histograms because we have the problem that we don't know the dimension of these eigenets, and we have learned our feature set. These are the results for all the graph kernel architectures. In yellow, we can see the state-of-the-art algorithms, and in green, we have the first 2 are the graph kernel with the structure, looking at the structure. The first is applying the spiral lemon kernel, in the second, the graphlet kernel. Then we have the soft feature alignment and the histogram kernel. We can see that basically all the algorithm performs better or almost in line with the best of the state of the art. We can notice that for the features of alignment, we have worst result on the EMDB dataset. This is because EMDB doesn't provide any node features in their dataset. And also we do a graph classification task on all the first 6 and a graph regression on zinc dataset. And on graph, these are percentage 0 to 100, and on graph regression, smaller is better. My last project I will present is Landmark Variational Autoencoder. This is a collaboration with the University of York. I worked with professors Richard Wilson and Edwin Hancock. So let's see what are autoencoders briefly. Autoencoders are a particular field of deep learning techniques. They are in the categorization of unsupervised algorithm, but this should be better to say that they are self-supervised because they learn from their decoding step. Also, they are of three main they are composed by three blocks: the encoder, the decoder, and the latent space. Basically, we want to have an input data, compress it in the latent space, and then we can use it for going through a very compressed channel or some limitation, and then we want to decode them. Or we can also do this whole operation to have to lose parts of the input data to have a better understanding of it. The variational autoencoders are a subset of autoencoders in which they aim to solve basically all the big problems of autoencoders, such as overfitting the training data. That is very usual when we are using autoencoders, and they don't have autoencoders don't have a natural way to model a synthetic. The basic difference is the ability to provide continuous data or a range of data in the latent space. Usually, we have that the latent space of variational autoencoder is summed by a normal distribution, and we have a lot. In deep, we will have some deep techniques to provide them, because it's not very easy. There are some tricks that can be applied. There are currently from tricks they came up as theory. However, for variational autoencoders, it's difficult to use graphs. Graphs are difficult to use in every space. I saw in my 3 years of PhD. There are two ways for encoding and decoding graphs. One is encoding on nodes, in which we have a latent space of the vertices and do a dot product for the decoding. In this kind of technique, the problem is that the latent space grows as the graph is bigger. And also we need to resolve the correspondence between the vertices at the decoding phase. The other technique is to decode, to encode to a fixed size in the latent space. We will add that the decoded graph will be isomorph to the original graph, but we have the problem that the graph matching will be at the training time. So when we are doing the encoding the latent space. What we proposed, our novelty was to combine these two methods. Basically, we want to pre-align the graphs, train a permutation covariant of the embedding, divide the graphs by landmarks, and use a unique alignment for each local cluster that we found. And then we will have the latent space that will be fixed. But we don't have to do some alignment because we have already the alignment ready because we have we did the encoding the latent space with similar graphs. This is translated to have a classifier that runs alongside the encoder that will help the encoder and also in the reparameterization part. And this seems to work. These are our preliminary results. I was able to accomplish this last week. We worked currently on the MUTAC dataset. It consists of 188 graphs with 2 graph classes. The results are quite encouraging. Usually on variational autoencoders, we work with we do our computation to have an outcrop curve and an average precision. From the baseline, it seems that from these results we have an increasing of 10%. So let's hope that it will remain this way or even better. So this is the end of my seminar. Thank you very much. And if you have questions.
So, questions? The IMDb was the Internet Movies Database.
Yeah. Yes. Yes. There are 2 different data sets of
these